Welcome back to Machinist Made. Today we are going to go over how to use the adaptive clearing. Some of you may know it as high-speed machining, others may know it as tricoil milling. So today we're going to go over simply how to do that. Up in the tab under manufacturing, you'll find 2D adaptive clearing. Obviously we're not going to use a 2-inch face mill. That was from the last tutorial. We're going to change over to a 3/8 diameter end mill. So all the tools that I'm using again are from the Fusion 360 library. We can go to milling tools, flat end mill, 3/8. We're going to be doing aluminum roughing, mash select, and we now have our tool. One thing to take in note from the feeds and speeds is this chip load right here. We're going to need to know what this number is. That's going to be later on. I want to show you where that's at. First thing we need to do though is select our geometry. So there's a lot of geometry on here, but the first thing we're going to do is the outside of our part. Now I know there's a step here, there's a step here, there's a window. We're going to do the outside of the part and that first step because both these can be done together and one doesn't interfere with the other one. We're going to go to our heights. And like I did in the last tutorial, we're going to change our clearance height to 0. Again, this is for simplicity of the program. The next thing we're going to do is go into passes. And this is where high-speed machining really comes into its own and how to know these parameters. Start with our tolerance. I'm going to change this to 5 thousandths. That's going to allow the program to run slightly faster. My optimum load is going to be 20% or just shy of 20% the diameter of my end mill. So I'm using a 3/8 end mill. In the world of perfect, it would be 74 thousandths and some tenths. But I'm going to simply use 70 thousandths. I like to keep my optimum load numbers normal. I do not want to rough both ways. Roughing both ways allows the cutter to cut climb cutting and then comes back in conventional mills. If you conventional mill on most machines, you will snap your end mill, especially if it's this small. If you had a 1-inch cutter or a 3/4 inch cutter or bigger, it would probably do it all day long, no problem. But on smaller tools, I highly recommend only climbing the part. Our minimum cutting radius is always 10% of our tool diameter. We are not using slot clearing because we don't need to. We're not slotting. Our direction will be climb. We don't need to do multiple depths since we're only using 20% the diameter of our end mill. We do not need to use multiple depths. If you were milling, let's say 10 times the depth of the end mill or 5 times, I typically use about 3 times. But if you're 5 times the depth of the diameter, then yeah, I would probably look at multiple depths. But for what we're doing, we're going about 700 thousandths deep. That's only 2 times the diameter of our end mill. Plenty enough. For our stock to leave, since we've done a tolerance of 5 thousandths, we want a radial stock of 10. We've told it plus or minus 5. We only need 5 thousandths to come back and clean up. We do need to turn smoothing on, and our smoothing needs to be roughly 1 thousandths on most controls. What this allows, actually Fusion has a really great diagram in here. See where smoothing turned off and smoothing turned on? You see where smoothing turned off on all them dots? It doesn't fill in any radiuses in, and this can beat the machine to death, especially if you don't have high-speed look-ahead. Some companies call it high-speed look-ahead. Some people just call it high-speed machining. Some people call it adaptive tool pathing. It's long terms for it doesn't beat the axis to death, and it can do some of its own math. So you do want to make sure smoothing is turned on. And feed optimization, you can go in here and kind of tweak and get a little bit more out of your program. I'm not going to do that on this. I'm not going to go that in depth on this tutorial. The last thing that I will do though is go into linking, and again, this is the second tab that's the most important when it comes to high-speed machining. My retract policy is going to be minimum. High-speed machining mode is going to be always use high feed. My machine can do 500 inches a minute in high feed mode. My maximum stay down distance There again, there's a diagram here. Anytime you need to know what something is, just hover over it. Fusion 360 has this wonderful diagram. It will stay down basically 1 7/8 of an inch. Minimum stay down 78 thousandths. That's fine. Stay down level. I'm going to go most. I want that end mill to stay at full depth as most as possible. My lift height. Remember I said how the chip load was going to be important later on? This is it. I just need to make sure my chip load is lower than my lift height. I don't want to drag a chip back across the surface, and I don't want to pick a chip up and have it stuck to the bottom of the end mill when it goes to its next depth. No engagement feed rate. Again, that's going to be 500 inches a minute. Leads and transitions, 10% of the tool diameter is perfectly fine. It's what most tool manufacturers recommend. I will do a helix entry simply because there's no hole there. It won't do a helix on the outside of the part. It'll only do helix with inside the body of the part themselves. 2 degrees, that's fine. That's not going to hurt anything. And the diameter and the ramp all that stuff's fine. Fusion will automatically figure this stuff out for you. You don't have to do much from that way. But typically you would do 90%. So if your tool is 375, you would do the tool plus 90%. That gives you your helical diameter. The only thing left we have to do in here is simply click OK. Tool path, it's going to kick out, outside of the part and the inside of the part. Now there is 2 more examples on this part that we do need to cover when it comes to adaptive. I am lazy, so I like to not have to change as much stuff as possible. So my next step is going to be right-clicking on adaptive and duplicating the process. Then I'm going to right-click on that new process and click Edit. Then the only things I have to do is change my geometry to the bottom and change my starting height. Now, my top height in this instance is going to be minus 0.3. I know this does not feel right starting below the surface of the part, but if we don't, we're going to get 300 thousandths of helical entry that we don't need. This is wasting time. But the good news is that's all I have to change. I can simply click OK. See how that helix is starting below the part? Then we've got the window to do. Again, right click, duplicate, edit that new process, go to my geometry, select new geometry, go to my heights tab and change this to minus 0.5. Click OK. Now we're saving a 1/2 inch of helical entry. And helical entries take a long time, so this is saving some serious time on your overall machine time. And bonus of that, it gives you full control over each and every pocket within the program. So now let's simulate this part and see what she looks like. There's our face build from our previous video. It's coming in. It chose to do the inside profile first, which is fine. I'm going to fast forward a little bit. It's going to the outside. Then it came down to the next one. And I want you to notice, whoop, if I get that pause right. I want you to notice when it came in, it dove down before starting its helix. It saved 300 thousandths worth of helical time. Same thing is true for the bottom pocket. Look at all the time that it's saving by not coming in. And I can even tighten this up more. It's doing what, 2.5 passes. I could tighten that up a little bit more to make sure that I'm not wasting any valuable machine time. Remember, machine time is money. If you're doing this for a living, or somebody's expecting you to do it for a living in their shop, they want to get the most out of the machines. They want to get the most billable hours out of the machine. So this is how you do that. This is how you are able to produce a more cost-effective part. that concludes it for this demonstration of 2D Adaptive. If you've got any questions, comments, concerns, please feel free to put them down on the bottom. Also, make sure you like and subscribe. YouTube loves it when somebody likes a video.